Finally, let me talk a bit about variants of the principle of inclusion and exclusion. Sometimes these variants are more useful. So most importantly, here is the weighted version. So in the principle of inclusion and exclusion, let me again use this form. We have a finite set, a bunch of subsets, and on the left-hand side, we count the elements that are not in any of the subsets. And on the right, we are counting the elements that are in some of the subsets. Now, instead of counting, here is one thing you can do instead of counting. Let W of X be, let W of X be a number for each X in U. Then, instead of taking this number, you take the sum over all X and U that are, you're just copying these conditions that are in none of the subsets, sum of W of X. So, and similarly here, sum over all X and U that are in the AIs for all I and I, W of X. And yes, one nice thing is the formula becomes shorter this way. So why is this? I claim that this is a generalization. I call it the weighted principle of inclusion-exclusion. Why is this a generalization? Because if all the W's are 1, then the sum is just the number of such X's, and this sum is the number of such X's, and you get the old form back. And actually, this is a bit easier to prove than the special case, because in a way you kind of you know what to do. On the left you have a sum of W's. On the right you also have a sum of W's with these coefficients. So the very logical thing is to basically check how often a given W of X appears on either side. You check that it appears the same number of times. And that's not very hard. So see the notes for the proof. For all the proofs, including the ones of the above versions. So this weighted version is particularly useful when you want to give some numbers in a way better treatment or higher weight. W stands for weight, of course. And in particular, it's useful for proving various algebraic identities where so these numbers don't have to be integers. So if this is like square root of 2, you could never find this by just counting. But this is called, but if you sum weights, you can get a lot of terms. So there are some other versions, which I'm not even going to prove in the notes. So let me just mention them. Here is one. Let U be a measurable subset of a measure space XA mu. If you haven't had measure theory, you can just say let U be a reasonably nice subset in an n-dimensional space. Let A1, A2, AN be n measurable subsets of U. And if you don't know measure theory, again, you can translate measurable as nice. Let W be a measurable function on X. Actually, on U is enough. Then the integral of W over the complement of the union, so basically over the points that are in none of the AIs, equals the sum of -1 to the I to the size of I, the integral over this intersection. This looks complicated, but really it is exactly this statement, except I've replaced the sums by integrals. And this conditions, this measurable condition, measurable function, this is just saying the integrals are well defined. You cannot just integrate some random function, but generally everything useful in life you can integrate. And then the theorem is true. And here is basically a way to restate it in terms of probabilities. Let E1 and so on En be n events in a probability space. Then the probability that you have neither of the events, so neither E1, nor E2, nor E3, and so on, nor En, that probability, you can again get this by summing over all subsets of n, the probability of EI for all I in I. In the case when the probability space is discrete, this is again a copy of this statement. Well, rather a probability space is finite. If it's infinite, this is basically this integral, because this is how probabilities are really defined. And you might have seen this in the probability class. I'm not going to prove this. In a way, these things are, if you have seen the proof of this here, the proof of this here is going to be the same argument, plus, of course, some analysis to make sure that all the sums, all the integrals are well defined. It's not going to be much more complicated. So much for the principle of inclusion and exclusion. I'm feeling sad for not giving more examples, but you will actually find a couple on the homework sets. And there is also, Googling will also give you a lot of other examples. I'm skipping the next section, which is about extremal combinatorics. Extremal combinatorics is about questions that are not saying how many things satisfy this property, but more questions of like how many things can you pick at most that satisfy a certain property. For example, how many subsets of a given set can you pick so that no two of them will be subsets of one another? Or how many integers can you pick from a given interval such that no two of them will be consecutive? Now, this one you have seen, it's about Laconer subsets. How big can a two Laconer subset be? But there is a lot more of such questions to ask. And if you're interested, section 7.9 in the lecture notes studies a couple of them. With this, I finish the section on the chapter on enumerative combinatorics.